Hi, welcome to a video podcast on stable and unstable nuclei. In this video podcast, we're going to have a look at what's inside the nucleus of an atom. Once we've established what's inside the nucleus of an atom, we'll have a go at understanding how it is that the nucleus of the atom stays together in a stable configuration. Most of the nuclei of the atoms in this room around us are completely stable and have been in existence, as far as we know, for billions of years. And from the limited knowledge you currently have of forces, that's a surprising result, because we know that protons are both positively charged, and therefore there must be a massively strong electrostatic repulsion between the protons that exist in the nuclei. They're both very small regions of positive charge. When you bring two positive charges together, they repel each other. However, there must be something else going on, otherwise nuclei simply wouldn't exist. And there's another force called the strong nuclear force, and the strong nuclear force attracts every nucleon, every neutron and proton, to every other neutron and proton, regardless of electrical charge. So in this nucleus here, which you should recognise as a helium nucleus, a helium-4 nucleus, 2 neutrons and 2 protons, it's entirely held together by this strong nuclear attraction. But the strong nuclear force is a very, very different force to, say, gravity or the electrostatic force, and then in that it's not a long-range force. If you imagine maybe the chair or whatever you're sitting on, it's full of nuclei, and those nuclei in adjacent atoms are relatively close together, certainly very close together in everyday terms, about 10 to the minus 10 meters. But there's no attraction between the two nuclei next to each other in the chair that you're sitting on, because if there was, all the nuclei would clump together and the chair would disappear into just a tiny little lump. Similarly, it can't also be the case that we only have, just going to draw out our nuclei again, we can't only have attraction between the particles in the nucleus. Because if there was only attraction, if all of these particles had a force, a net force on them towards all the other particles, the nucleus would get smaller and smaller and smaller and disappear into a point. And even though the nucleus is very small, we know that it's not a point. And the strong nuclear force matches this description at distances that are greater than 3 femtometers. So femto is one of those little suffixes that we use in measurements. It means 10 to the minus 15 meters. So at distances of greater than 3 femtometers, there is no nuclear force. At distances which are less than 3 femtometers, but more than 0.5 femtometers, then we get attraction between nuclei. However, at distances which are less than 0.5 femtometers, then the strong nuclear force will cause repulsion. So if we look back to here, the nucleus is small. These nucleons are within 3 femtometers, so they're feeling an attraction. But as they get close to each other, as they get closer, they start to repel again, and they're sat nicely in equilibrium here with balanced forces. So the strong nuclear force and the electrostatic force are providing just as much repulsion as they are attraction.